Okay, this is the week 2 video for AC theory. Last video we talked a little bit about inductors and capacitors with regards to Z impedance, and we talked about the fact that Z impedance is made up of reactance on the one side, resistance on the other side, and reactance itself is made up of capacitive reactance, that is the reactance due to a capacitor in a circuit, and inductive reactance, which is reactance due to an inductor or a coil in the circuit. We're going to talk about coils, inductors today, so I want to go over that a little bit more. Please take a look at the document that I gave you. If you've printed it, great, get it out. If you haven't printed it, if you've got it electronically, take a look at it if you can while you're watching this video. On that document, I have a formula that's incorrect on the document. I forgot to fix it this term. And it says L equals 2 pi FL. The correct formula for inductive reactance, X sub L, should be X sub L equals 2 pi frequency times inductance. We call this formula 2 pi fly. X sub L equals 2 pi fly. That's a really easy way to remember that. And we'll go over that a little bit more. But I want to talk about inductors and talk about what happens when we put an inductor in an alternating current circuit. If you watch the videos that I gave you last week, especially the ones, the PDS videos, there was some really good information on that. They gave you a ton of math. And some of their math isn't exactly the way we do it. She refers to voltage as E for EMF. She uses a big E like that, like the fancy scientists use. We've been just doing E for voltage. But she'll speak of voltage as EMF, which is the same thing, and you should know that. Electromotive force is voltage. So some of her formulas may have looked a little bit funny to you if you watch those videos, but she talked about what happens when we put a coil in a circuit. A coil has self-inductance. We learned last term when you charge a coil, an inductor, it charges up because as I turn a switch on in a DC circuit, I am changing the amount of current that's happening. And as I change the amount of current, because of the physical makeup of that coil, that current changing has lines of flux, magnetic lines of flux that expand around that wire. And because of the physical manifestation of the shape of this wire, which is now a coil, those lines cross the wire itself. When that happens, it produces something called back EMF, or reverse EMF, or reverse voltage, or back voltage. It's essentially the coil pushing back when current changes. So in DC, the only time the current changes is between off and on. I turn something on, boom, I've got a current change. And so we get that, you might remember that curve. If we were to graph the current, it starts out as 0, and after 5 time frequencies, which we can calculate based on the inductance and the resistance in the circuit, we can figure out how long it takes to get to that top DC voltage, or approaches that top DC voltage. You may or may not remember that. That's the same thing that's happening in an AC circuit, except that instead of just turning something on, we're turning something on and off, on and off, on and off, 60 times a second. In fact, on-off, if you think of it, because we go both directions, 120 times a second. Well, we get that full sine wave cycle 60 times a second. So this coil starts out pushing against the change of current going the one direction, and suddenly it's got a change of current coming the other direction, and by that point it's already charged, so now it's releasing current back that way. Now it starts pushing against the change going the other direction, because either the lines of magnetic flux are expanding around the wire, therefore crossing the conductor, which induces a voltage which pushes a current, or they are compounding, they're compacting, they are coming back to the wire because the current has been changed or is moving the other direction, at which point they're crossing the wire again, and they're creating an opposite effect. So whether the flux is crossing the wire in this direction or crossing the wire in this direction, either way it is changing the amount of current that can flow in the direction of current that can flow in the push that this coil is putting on the circuit. And that manifests itself in a couple of funny different ways. Let's go ahead and turn this into a circuit. So we'll leave that as my coil. I usually draw a coil a little bit tighter than that. We'll leave that as a coil right there. Now obviously we're going to have some resistance in this circuit. If nothing else, it'll be the resistance of the wire that we're using, or possibly the coil itself, because the coil is just made of wire, so it has a resistance. Let's go ahead and put an AC voltage on this guy. Now what's going to happen as this AC voltage turns on and turns off, it's going to induce a voltage back on itself. I turn it on, obviously there's a voltage drop between here and here and here. If that's positive, negative, this is grounded, so we can call this 0. When I turn this on, I've got a voltage. But as soon as the current starts to flow, this guy's pushing back against the current. And depending on the frequency, which in this case is 60 Hertz, and depending on the inductance of this coil, it's probably not going to charge all the way up by the time that current reverses. So this is going to be pushing back against the one direction. The current reverses, it starts pushing the other direction. Either way, it's making that current lag behind the voltage. The voltage is always going to be out in front of the current because it's the voltage that pushes current through this. It's the change of current that makes this push back with a back voltage and push back against that current. So we're always going to see the current lagging in a coil compared to the voltage. And there's a mnemonic for that. You may have seen this on your sheets, ELI and ICE. And we remember that as Eli the Iceman. We're going to go over this some more later, but let me introduce it to you right now. I've got two flavors of circuit that this can talk about. It can either talk about an inductive circuit. Remember, inductance is L. That's the symbol we use for inductance. Or it can talk about a capacitive circuit. A capacitor has C. C is capacitance. So if I figure out which circuit I'm dealing with, I know whether to use Eli or ICE as my mnemonic. Well, this is an inductive circuit, so I'm going to use Eli. And Eli tells me that the voltage leads the current. The voltage happens first, and the current reacts to it in an inductive circuit. And this is an inductive circuit because it's got an inductor in it. And right now I don't have any capacitors in it, so there's no capacitance in this circuit. So I'm going to use the rule Eli. Voltage leads current, and L isn't for leads, it's just the order of this. Voltage is ahead of current, current is behind voltage. Obviously, in our culture, we read left to right, so as I read this left to right, E is before I, voltage is before current, voltage leads current, or saying the same thing a different way, current lags voltage. That becomes important, and you will see why. But I wanted to enter that in right now. So, I've got a series circuit, and I've got some sort of inductance here. I'm going to go ahead and throw some numbers up here just so we have something concrete to work with. We'll work through this first one. I'm going to go ahead, and I'm making these up right out of nowhere, so I'm probably going to need to run and get a calculator as we do this. I'm going to go ahead and say, well, first of all, what's my unit for inductance? Well, it's in henries, so I need to put some value in henries to this inductor. I'm going to go with millihenries. I'm going to say 75 millihenries is the value of that inductor. Now, that's not its reactance. I need to solve its reactance, and we'll do that in a second with this formula. And then over here, I've got resistance. And on my resistance, I'm going to say R equals 50 ohms. Just come up with a number. Just making numbers up. And I suppose we should have a voltage here. Let's go ahead and make it 100 volts AC. Obviously, we'd be working with 120 or 240 or 480, 277, one of the voltage flavors we know. But we're going to throw 100 up there because this is just theory. And we'll take a look at that. Well, the first thing I need to say to myself is, this is a series circuit. So, in a series circuit, we learned some rules back in DC, and those rules all apply. In fact, they're even more important now. The first rule of a series circuit is, we know it's a series circuit because there's only one current path. And there is still only one current path. Don't look at my little ground here, it doesn't count. Every electron has to go through the coil and then go through the resistor to return to the voltage source. There's only one way for them to do that. So it is a series circuit, we know that for sure. In a series circuit, I know that the value of the current is the same everywhere. And when I say value of the current, I mean the actual quantity in amps of the current. If I decided that I had 1 amp here, I'm also going to have 1 amp here, 1 amp here, 1 amp here. The other interesting thing to know in this one, and this may not make sense to you yet, but it will in a second, is that in a series circuit, the current is in phase with itself everywhere. Now, we talked about the current and the voltage being out of phase with itself in this because of that inductor. Everywhere that we are, the current is in phase with itself. Keep that in mind. Store that in your noggin for a second. You're asking yourself right now, what is he talking about? It's going to make sense in a second. So let's go ahead and solve this a little bit here. I'm going to have to figure out what my total, well, resistance usually for a series circuit, but now I'm dealing with something that doesn't have a resistance, it's got a reactance. So I'm going to need to figure out how to solve for this reactance, and then how to figure out the total impedance, Z, for this circuit. And once I found that total impedance Z for this circuit, I can go ahead and solve the circuit the same way we would any series circuit. Once I've got the total impedance, I can figure out my total current. Once I figured out my total current, I can use that current individually at each of these components, and I can solve the voltage drop here and here. There's going to be a fun thing that happens when we do that, but let's go ahead and do that. So 75 millihenries, I'm going to use this formula. Again, this is the formula for solving inductive reactance, X sub L. I'm going to call it X sub L all term. Later I'll be talking about X sub C. If I ever get my tooth fixed, I'll be able to say that a little better and not sound like Opie. But for now, X sub L equals 2 pi fly. And that's one to memorize. There's no reason you shouldn't be able to remember 2 pi fly. Now, 2 is 2, the number. Pi is the Greek symbol that we use for the number, which is 3.1415. I can't remember the rest of it. That has to do with circles and figuring out the geometry of a circle. It's a number that some ancient Greek came up with a long time ago. But we use pi for that. Pi not to be mistaken with omega for ohms. Some of you draw a symbol for your ohms that looks an awful lot like pi, and you might want to be careful of that going forward because those are two completely different things. Ohms is the unit for resistance. Ohms is also the unit for X sub L and X sub C and Z. Ohms is the unit for impedance. Ohms is the unit for inductive reactance and capacitive reactance. We'll cover that in a second. So 2 times pi times F. What's F? Well, it's frequency. 60 hertz in this case. So we're just going to dump 60 into this formula when we do the actual math. And then L is the inductance. I've given you the inductance here in millihenries. So when I dump it into that formula, it's going to have to be 0.075 henries, because a millihenry is 1/1000th of a henry. And I'm going to walk toward the camera, excuse me, while I grab my calculator so I can actually do this math problem. So if I'm calculating X sub L in my calculator, first of all I'm going to make sure it's on and clear. I'm going to go 2, and I don't even have to do a time symbol for pi because it's a symbol. If I just put it next to it, it knows I'm multiplying it. So I'm going to go 2 pi. I have a pi symbol. It's right above the caret, we call that raised to the power up button. So it's 1, 2, 3, 4, 5, 6 up from the on button. So 2 pi, and then I can just dump in 60. Now I could also go 2 times pi times 60, but up 2 pi 60, I'm there. And now I do have to multiply because I'm going to be putting in another number times 0.075. And that enter gives me a number that makes sense to me. It's 28.27. So I'm going to put 28.27 ohms. Everybody do that math on your calculator during this video or afterwards, and make sure you can do that math and it comes out the same. You should dump in 2 times pi times 60, because we're at 60 hertz. If I didn't note that, just assume 60 hertz. That's our frequency. That's how many times a second we get that sine wave, 60 hertz. So go ahead and use 60 for F unless you're told not to. Now in the military, I know some of you have military background, some of the big motors on ships and things use 400 hertz. In England and in parts of Europe, they use 50 hertz, 50 hertz. In America, in most of this hemisphere, in most of the Western hemisphere, I should say, we use 60 hertz. And somebody can correct me if I'm wrong on that, but I'm pretty sure everywhere that, I know in South and Central America it's all 60 hertz. So we'll use 60 for that number, and then for L, I dumped in 0.075. Boom, hit the enter button, got 28.2743, and I just rounded it to 2827 ohms. Notice I did ohms. So here's the thing. This is a voltage divider, because it's a series circuit, right? And so I know I'm going to have some of the voltage here, and I'm going to have some of the voltage here. And now back to Kirchhoff's. Kirchhoff would tell me that those two are going to add up. As I do a loop, those voltages add up. But we've got kind of a right turn that we have to make here on Kirchhoff's, and that is because this is a voltage divider, and because this component actually has back voltage that's produced because of the change in current, it's going to have a voltage that is out of phase with this voltage. And now earlier I told you the currents are all in phase, and now I'm telling you something's out of phase. Well, what does that mean? Well, remember, we can graph a sine wave, right? This is my y-axis. Did I do that wrong last time? X and y-axis? This is my y-axis. This is my x-axis. This is time. This is now. This is 16 milliseconds in the future at 60 hertz. This is some voltage, up or down. This might be the voltage at the source. But because this guy's producing its own voltage and pushing back, those two voltages combine to create a different voltage at this unit. And what we might find there is the voltage at that is actually out of phase with the source voltage. If I was to measure the source voltage, I might get this sine wave. If I had an oscilloscope that could actually measure these things. If I'm just on a multimeter, you're never going to know about the phase. But I measure this, it'll give me this first sine wave. And I should have done these in two colors, but you can see. If I measure here, it might give me the second sine wave. Now here's the cool thing. A resistor is always going to be in phase with the source. A resistor does not lead or lag. A resistor is always in phase with the source voltage. It may not, in fact, it won't be in phase with this inductor. If we had a capacitor in here, it wouldn't be in phase with the capacitor either, but we aren't getting there yet. So for now, I've got these two voltages that are out of phase with each other, but my current is in phase. But the first thing I need to do is figure out what my Z is. And the fact that I've got out of phase voltage here and out of phase voltage here with the same current means that not only will my voltage be out of phase, but the ohms of reactance will be 90 degrees, in fact, out of phase with the ohms in the resistance. We can model those as something that has a 90-degree relationship with itself. And I want to talk some more about that after this circuit, that 90-degree relationship, and talk about how we figure that out. I'm going to do it first, and then we're going to see why afterwards. So I need to go ahead and model this as two things going on here. This is kind of vector math, and it's kind of Pythagorean's theorem. Now the book, if you read on AC, and if you read about the inductors, if you read the chapter that was assigned for this week, off the top of my head I can't remember if it's 17 or 18, I think it's 17. But don't quote the video, look at the Moodle, because it'll be right there. You'll see, it'll give you some explanation about why there's a 90-degree difference between the ohms in the reactance and the ohms in the resistance. It has to do with the way that inductor works and pushes back. So I'm going to go ahead and model this as a 90-degree triangle. I hope somebody got the homework or the extra credit right about who said, what were the two quotes were, all models are wrong, but some are useful. That's quote number one. And the second quote, which I think essentially says the same thing, was, all art is a lie, but it shows us truth. I think that's what it was. It shows us beauty or shows us truth? I think it shows us truth. All art is a lie, but it shows us truth. So my model is art. Maybe, maybe not. It's definitely a lie, but hopefully it'll show us the truth. So I've got this 90-degree relationship. And let's go ahead. I'm always going to put the resistance this way. And for this class, I'm going to go ahead and put the X sub L this way. So I'm modeling these ohms and these ohms. Now I've already drawn them wrong, right? Because I should have drawn the R like twice as long as this. So not to scale, right? Now I can figure out what these two vectors, what their equivalent vector is by solving the hypotenuse. And I know I can do that because if I have two right-angle triangles, and this won't be on the test, but it's good to know. If I have two right-angle triangles and I put them back to back with their hypotenuses, I've got a rectangle. And one of the things we know about rectangles from 8th grade geometry is that the diagonals are equal. If I have a true rectangle, which is just any shape that's got 4 right angles to it, is a rectangle, right? A square is a rectangle. It's a special case. It happens to be equal sides, all 4 ways around, but it's still a rectangle. Any rectangle, the diagonal this way will be the same as the diagonal that way. So by solving this diagonal, which we call the hypotenuse, I'm also solving this resultant vector between these 2 vectors. And I can do that all without stepping into vector math. And that's a fabulous thing. If you look at the vector math unit in this book, it's not something I want to teach, and it may or may not be something you want to learn. I don't have enough time to teach it, but this is a good way around it. Pythagorean's theorem, we know how to do Pythagorean's theorem. That's what I'm going to do to solve this hypotenuse. So I'm going to call this hypotenuse z. So instead of a squared plus b squared equals c squared, I'm going to say my x of L squared plus my r squared equals my z squared. And then I'm going to go ahead and do the mathematical gymnastics, which I asked you to do with c before, and I'm going to say that z equals the square root of x sub L squared plus r squared. I'm going to dump that into my calculator to say z equals 28.27 squared plus 50 squared and take its subroot. So let's run through square root, not subroot. So in my calculator, 28.27. Play along at home. Got your calculators out? Get your calculator out. 28.27 squared, which is the button to the left of the 7, plus 50 squared. And I'm going to hit enter. Boom. And it gives me a big, ugly number, 3,299 and change. And I don't even care about that number because what I'm going to do is just go second square root. And if I just hit enter, it says syntax error, so I'm going to clear that. Second square root, second answer. By hitting second answer, it gives me that last number that I last had up on the calculator. And you got to keep track and make sure you didn't do some other math in between. But as long as it's the last number you came up with, enter. And I get 57.438. And I'm going to round that to 57.44. So I'm going to say that my z equals 57.44 ohms. It's still ohms. I've taken ohms in one direction and ohms in another direction, and I've come up with their resultant ohms. Okay? You're going to say to me, how is it that I can't just add these up? Well, you can't. So I've got one set of ohms here, I've got one set of ohms here, I've got my voltage. I should be able to solve current, right? I've got Z. I'm going to erase some of this. You can always rewind to get back to it, right? That's the beautiful thing about that. Class, people are always like, oh, erase it yet. Okay, so I'm going to solve for I. So I always equals E over R, right? But I don't have just R anymore. I've moved up in the world, and I have Z. Because Z is all of this plus all of that. 90 degrees from each other, but I come up with Z. So my formula then lends me to say 100 volts divided by 57.44 ohms. And that's going to give me my current. So when we do this, I'll dump this into the calculator, but remember that your current is the same everywhere because it's a series circuit. You're never going to divide the current in a series circuit. You're never going to have to worry about a Pythagorean triangle on the current in a series circuit. The Pythagorean relationship in this circuit is, first of all, between the ohms. And we'll see where else it is in a second. So I've got 100 divided by 57.44 equals, where's my equal sign? There it is. I get 1.7409. So I'm going to say 1.74 amps. So I don't want to round 0.9 up to 1. I want to round it down. So 1.74 amps. That's my current. Say it again. I know I said it 18 times, and I apologize if I'm boring you with it. But it's really important to know that this is the same current everywhere, and that current is in phase with itself. If I was to measure the current here with an ohm meter, or with a scope, an oscilloscope, and measure the current here, I would get two sine waves that might not have the same magnitude, but they would be in phase with each other, right? No lag there at all. When they cross zero, they cross zero. When they're at their high point, they're at their high point, right? Both of them together. That's called in phase. My two currents are going to be in. Now, They aren't two currents, right? They're the same current because it's a series circuit, but that's what it means to be in phase. So that was a bad example showing them out of magnitude, because obviously the magnitude would be the same current. That's what happens when you shoot from the hip. So 1.74 amps. I'm going to dump that in up here. So I've got 1.74 amps is my I at the L, right? So my notation for this should be, use my thumb to scratch it out, I at the L equals 1.74 amps. And my I at the R, in this case I only have one R, so I don't have to call it R1. I at the R equals 1.74 amps. Now I can solve my two individual voltages, just like every other series circuit we've ever done. E equals I times R, and my I is 1.74 amps times 50, and I'm going to clear this instead of using that nice big number, which I probably should have used because it would have been more accurate, but I want to do it so you can follow at home. 1.74 times 50 equals 87 volts. And over here, I'm going to go 1.74 times, whoop, hit the wrong button, times 28.27. Make sure I did that right. Enter. I get 49.19. 49.19 volts dropped across this. So if I took my multimeter, my nice RMS multimeter, and I put it here and here, I get 49.9. If I put it here and here, I get 87. Now what's the first thing you notice about that? What happened to Kirchhoff's? How could I get dropped 49.19 volts here, and then I got to drop another 87 here? I don't have 87 left to give. Well, you do, because these are out of phase with each other. And in fact, they're 90 degrees out of phase with each other. Check this out. Remember that triangle I drew? There is a Pythagorean relationship between the voltage at this coil and the voltage at this resistor. Now here's a really good way to memorize this, to remember this. You don't even have to memorize, just remember this. You already know this is a voltage divider. It's whatever kind of divider the circuit is that is also where the Pythagorean relationship is. In a circuit I have some total amount of resistance, or in this case impedance, in ohms, and it gets divided between these two different things, right? In a series circuit. In a parallel circuit it wouldn't work that way. I have a certain amount of voltage in a series circuit, and that voltage gets divided in a series circuit. Those are the things that have the Pythagorean relationship in a series circuit. Now current does not get divided. I've got the same current everywhere, so there's no Pythagorean relationship in a series circuit between the currents of the different things. So let that sink in a little bit. If it's whatever kind of divider it is, that's also where the Pythagorean relationship is. So voltage divider, Pythagorean on the voltages. Something that has resistances divided up in series, that's where the Pythagorean is, which we just demonstrated. Let's go ahead and look at this again with regards to the voltages. If I dump in my triangle, make my right triangle again, I'm going to do the resistive element on the horizontal. Over here, I figured out that that's 87 volts. That direction. I just told you they're 90 degrees out of phase with each other, and I'm going to prove it. Over here, I've got 49.19 volts. I want to solve my hypotenuse, because remember what I'm actually doing is solving that by solving this hypotenuse. To solve that hypotenuse, the hypotenuse in this case, well, we'll see what it's going to be. I'm going to say question mark equals the square root of 49.19 squared plus 87 squared equals. This is a great time to follow along at home with your calculators. Clear, clear, clear. Let's see. I've got 49.19. Whoop, whoop. You see, I already screwed up the number. 49.19 squared plus 87 squared. Always check, because I do it wrong a bunch of times, right? And if you do it wrong in the calculator, you might never notice it. And I'm going to go enter, and that gives me a number like 9,988 or something, some big ugly freaking number. And I'm going to go ahead and say second square root, second answer. and 99.99, actually 99.94